Alright guys, this video is going to talk about the distribution of the sample mean. Okay, a couple things I'm wanting you to get from this lesson. First thing is I want you to be able to describe the distribution of the sample mean with a normal population. There's going to be three key things that we're looking for whenever we're describing. We'll get to that in a little bit. And the second thing I want to be able to do is describe the distribution of the sample mean from a non-normal population. We've been talking about this normal curve and some of its properties and how we can use our z-table to find some probabilities. It's all going to kind of filter in to what we're doing this morning. So statistics such as x bar are random variables since their values vary from sample to sample. Anytime I take the average height of 5 students, I'm not expected to get the same x bar each time. All right? And so since I don't get the same thing each time, they have probability distributions. So in this chapter, I guess these next two lessons that you're going to watch, we're going to focus on being able to describe their distributions. Okay? And whenever I ask you to describe the distributions, what I'm looking for are three things: the shape, the center, and the spread. You'll hear me refer to that as the three S's, since they all start with an S, obviously, right? So the sampling distribution of a statistic is the probability distribution for all possible values. If I was to take the height of 5 students here at DHS, I want to get every possible average for those 5 students' heights that I can get. All right? And I'm going to put them all underneath the curve. So the sampling distribution of the mean is just going to be the possible values of all the random variables x bar that I can get from those 5 students' heights. Okay? And so we have to establish a size n, we have to have a mean, and we're going to have a standard deviation with these. So here's how I'm going to be doing it. Okay? This box is kind of in the way, isn't it? Does it move up a little bit? Oh. Yeah, we'll move it up a little bit. So first thing I'm going to do is I'm going to obtain a simple random sample of size n. And it can be of any size. I'm going to kind of play with that size here. I'm going to go really fast to the front part of this and maybe overteach it a little bit, but by the end I think it'll all make sense to you. Okay? And then I'm going to just find the mean of that size n. And then I'm just going to repeat. I'm going to go over and over and over again until I get the number of samples that I want from that size n. All right? So what I'm going to do is I'm going to take a bunch of pennies, and it says that the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 grams and a standard deviation of 0.02. Now, last week we worked with these numbers some, with this mean and standard deviation. We were able to do some z-scores underneath the normal curve. The difference this week is that we're going to be doing this with x bar. We're going to be doing this not with just the probability of maybe one student being at least 5'7", but we're going to do the probability that the average height of 5 students is at least 5'7". All right? So I've had a lot of time on my hands because you guys haven't been around. So I'm going to do 200 simple random samples of size n equals 5 from this population. So I got this big bucket of pennies right here, and I'm going to pick out 5 pennies, I'm going to weigh them, and I'm going to find their average weight. And I'm going to do that not 500, man, I don't have that much time, 200 times, okay? Not much math to show here, I'm just wanting to kind of show my point as to what's going to happen, okay? So here's all of the weights of the pennies. Whenever I took this sample of 5 of them. So like, I'm just going to randomly choose one right here. So I took 5 pennies and weighed them, and their average weight came out to 2.457 ounces. Right? And I did that for all these. That's how I got all these numbers. It took me a long time. Now, if I was to find the average of all of these weights right here and the standard deviation, just plugging in my calculator and doing some one variable statistics on it, I would get that the average came out to 2.46, So it didn't change from just the average weight of 1 penny. But here's what did change was my standard deviation came out to 0.0086. So it was smaller. If I make a histogram with this in some statistical software, it came out to look like this. Now, I would still call this roughly normal. If I draw a curve over the top of, kind of close to the top of all these bars right here, I see that it's forming a nice bell-shaped curve, symmetric, normal curve that we've been working with. It's kind of got some oddities in there, but overall, it's in no way skewed left or skewed right. I mean, it's closest to bell-shaped, I would say. So what if I change in? I'm glad you asked. I know you guys are asking yourself that. So I am going to change in. So instead of just doing 5 pennies, I'm going to do 20 pennies. And I'm going to do it 200 times again. So I'm going to get 20 pennies from my bucket. I'm going to grab them. I'm going to weigh them. I'm going to find their mean. I'm going to throw those 20 back in the bucket. I'm going to get a different subset of 20 pennies, weigh them. I'm going to do that 200 times. All right? Now, remember, just 1 penny, like we did last week, would give me these numbers. Definitely do a z-score with it. But what if I up it to 20 pennies? Let's see how my parameters change on that. Well, this is what my histogram looks like whenever I did it. A little bit better on this bell-shaped curve. It follows it a lot better. So upping the n to 20 actually helps me out statistically. I still got my mean to be 2.46. And I'm going to talk about how to get all these numbers in just a minute. So if you're like, where in the world is he getting these numbers? It's coming. It's coming. The standard deviation, it went even lower. All right? And so there's less variability if I have 20 pennies versus if I have just 5 pennies. So here's how I'm getting these numbers. I'm actually not weighing the pennies. If you think I'm that bored, or I'm just into math that much. I actually am into math that much, but I'm just not that bored yet, all right? But here's where I'm getting the numbers, okay? Getting the shape of it, I don't think is going to be very hard, but getting the center and the spread, the mean and the standard deviation, I'm getting it from these formulas, okay? So if I'm looking for the sampling distribution of X bar, my mean, as you just saw in the previous penny example, is not changing, all right? Whatever the mean weight is of 1 penny, I expect to get that if I weigh 5 pennies and average their weight. If I weigh 20 pennies and then average their weight. The standard deviation you saw, it got smaller. And here's how we are going to compute standard deviation. These formulas, I do not expect them to be memorized. Obviously not right now when you guys are home, but even if we come back before this assessment, these formulas will be on the board. For your final, these formulas will be on the board. You just have to be able to recognize them and know when to use them, all right? And so these are going to be the formulas that I use. And so we'll put these to work in just a moment. As far as the shape goes, remember, we're interested in the shape, center, and spread. The shape of it, like I said, if it's going to be normally distributed, then the distribution of X bar is also going to be normally distributed. Guys, you're not going to really have anything that's going to be left skewed or right skewed yet in an introductory level statistics class. So we're just going to simply say normally distributed on all of these. So let's go back to the pennies. Pennies minted after 1982 are approximately normally distributed with these parameters, okay? So I want to know the probability that in a simple random sample of 10 pennies, we didn't do 10, we did 5 and 20. So in this case, my n is going to equal 10. 10 pennies minted after 1982, we obtain a sample mean of at least 2.465 grams. Now, it doesn't really ask for the shape, center, or spread on this. I could definitely find it. I think I'm going to go ahead and find it since we're not with each other. And so, first up, I can definitely find my shape, or my center, I'm sorry. Okay? And so the center of this is not going to change. It's going to be this 2.46 that I have right here. Okay, my spread. Okay, to find my spread, I'm just going to take what my original standard deviation was, this 0.02, and I'm going to divide it by the square root of n, the square root of how many pennies I am weighing. And whenever I did that, I got 0.00063. And since that my original was normally distributed, I can go ahead and state that this is going to be normally distributed. So in the practice problems, when it says describe the sampling distribution, these are the three things I want. All right? I want the shape, I want the center, and I want the spread, the three S's. Okay? Now, on to this problem. Since I have something that's normally distributed, I'm expecting it to follow a bell-shaped curve. And right in the middle of this bell-shaped curve, it tells me that I should have 2.46. Well, I want to know the probability of getting a sample mean of at least 2.465. Well, 2.465, I'm not exactly sure where it'll be. I'm just going to draw it over here. I know it's bigger. So of at least 2.465, I'm wanting to know the probability that I get something bigger than 2.465 over here. Well, this looks very familiar to the quiz that we took last week. If it's normally distributed, I just need to find a z-score using these numbers that I found. Okay? Now, unfortunately, I don't get to use these numbers. If I was just wanting to know the probability of maybe 1 penny being heavier than 2.465, I would use those numbers. But I want to know the probability that my sample of 10 pennies got bigger. So I need to come down here and use my new numbers that I found. Okay, so I'm using those new numbers. 2.465 is the number I'm interested in. So that's going to be my x minus my mu. Well, my mu is not going to change. It's still 2.46. I'm going to divide it by the standard deviation. Careful, I want to use my new spread down here. My new standard deviation for whenever I'm using 10 pennies is 0.00063. I do my calculator magic with that, and I've got 0.79. Now, that's my z-score. That's not my probability. That's my z-score. So that means that I'm 0.79 standard deviations away from this center right here. To figure out what the probability is going to be, hopefully you're a little bit ahead of me. Yeah, we're bringing back our friend. Oh my goodness, what is going on? I am just jumping everywhere now. All right, we're going to get this. Just wanting to erase it. Let's try again. Nope. We're okay. We're okay. We'll just erase it. Whatever it wanted to erase. Got to exit out of that. And I've got my z-chart handy. Oh, it's kind of dark. My light's turned off. But looking at this z-chart, let's see, my z-score was 0.79. So I'm coming down to 0.7. I couldn't fit it all on here. It was too big. Let me change colors. 0.7. And hopefully you have your z-chart going across right here. I'm going to try to get it right. But it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I believe that number is 0.7852. Okay? 0.7852. So let's get off of this. Go back to my slideshow. Present. 0.7852. Now, remember, 0.7852 is going to be all this area to the left. Remember that your z-table loves area to the left. I want the area to the right. So to find my probability, I'm going to just come up here to the top. I'm running out of room down there. To find my probability that my x bar is going to be greater than, what was my number? 2.465. I'm going to do 1 minus that probability is to the left, 7852. And that should give me 0.2148. Recap real quick. I take 10 pennies, minted after 1982. I have a 21.48% chance that their average weight will be at least 2.465. I'm hoping you guys notice that there's not just a lot of change on this as far as what we did last week. All right, so clumping all this stuff together, I don't think it's going to be very hard. The only new thing you have to worry about is everything that's down here in this box, being able to find the mean stays the same, but being able to find a new standard deviation and then applying it to the problem. We'll do that again in just a minute. I want to talk about something that, that's just a solution. I already drew that. What if I have something that's not normal? This throws people off every year, and I'm not sure why. So I'm gonna take something that's not normal, and I'm gonna say rolling a die. If I roll a die, I have a 1 in 6 chance at either getting a 1, a 2, a 3, a 4, a 5, or 6. They're all the same. I have a 1 in 6 chance at getting all those. And so if I was to make a histogram with this data, it would look like this. Well, that's not a normal distribution. That is called a uniform distribution because it's uniform all the way across. Now, the average number I would expect to get is 3.5. So I can still come up with an average. I expect on average I should roll a 3.5 if I was to guess right in the middle of numbers between 1 and 6, which is obviously 1 plus 6 divided by 2, 3.5. And I get a standard deviation of 1.708. Don't get hung up on that right now, but I want you to see that the distribution is not normal. So I'm going to do some repeated sampling of this. I'm going to roll the die. All right, it says I'm going to roll the die 4 times. And I'm going to calculate what my mean roll is. So I'm going to roll it, I roll a 5. I'm going to roll it, I roll a 2. I'm going to roll it, I roll a 6. I'm going to roll it, I roll a 3. And I am going to do that 200 times, but for every 4 times I roll it, I'm going to add up what I got on those 4 rolls and then divide by 4. Okay? And I'm going to do this 200 times, all right? And then I'm going to repeat this. I'm going to do the same process, except for I'm going to roll the dice 10 times and then take the average of the sum of my rolls. And then I'm going to do it again. I'm going to roll the dice 30 times and then take the average of it, all right? And so made histograms for it. I already did all this, so you don't have to watch me do it. I already did all this. I was really bored counting pennies and rolling dice. It's been a great quarantine period for me. Look what happened to my uniform distribution whenever I started doing sample means with it. It's not perfectly normal, but man, it's closer to being normal and bell-shaped than it is right-skewed. It is a little bit right-skewed, but it's closer to being normal than being right-skewed whenever I roll the dice 4 times. Look what happens whenever I roll the dice 10 times and I average them. A lot more normal, right? Look what happens when I roll the dice 30 times and then I average them. Made a histogram from it. Even more normal. Here's what I want you to get from that. The mean's going to stay the same. The standard deviation, I'm still going to be able to find the standard deviation using the same formula that I did earlier. But by something called the central limit theorem, the shape of my distribution is going to become more and more normal as my sample size n increases. So while my sample size wasn't very big, it was 1 whenever I had the uniform distribution, as n becomes larger and larger and larger, I'm going to become more and more normal. Here's the key right here, regardless of the shape of the population. So if I start with something that's left skewed and I repeat this process and I increase n, then I'm going to become more and more normal. If I start with something that's right skewed, left skewed, normal, it doesn't matter what it is, my shape is always going to be approximately normal with the problems that we're going to be working in here. So let's do one more. So I really don't have to worry about it. As long as this end right here is getting large, I'm going to have something that's normal. What's large? Well, for right now, let's just say large is more than 10. All right, we actually have a test for it, but I'm really not going to worry about it too much. As long as n is, we'll say 10 or more, we're good. All right. Now, it says suppose that a mean time for an oil change at a, quote, 10-minute oil change joint is 11.4 minutes. I really didn't want to throw anybody under the bus on this, so I just left it, I left their name out and just put this in because it actually takes them 11.4 minutes on average to change your oil. All right? So don't want to get in trouble with anybody, so that's where we're going to stay at with that. All right? Now, on average, if someone was to come in, yeah, it's going to take them, on average, 11.4 minutes for them to change the oil, but the standard deviation for it is kind of large, 3.2. So I'm going to take the next 35 cars that come in right here to the oil change, and I'm going to describe the sampling distribution with them. Remember, whenever we're describing, I want the 3 S's. That looks weird. The 3 S's. I want the shape. Oops. I want the shape. I want the center. Or maybe it's the center. I don't know. And then the spread. Spread. I almost couldn't spell spread. Shape, center, and spread. Okay. Now the shape. All I'm going to do is look. Let's see. I'm above 10 right here. If I'm above 10, it doesn't matter if I start off being normal or non-normal or uniform or left skewed or right skewed, my shape is going to be normally distributed. I'll go ahead and throw you a hint. If I'm asking you shape in this class, say normally distributed. Actually, we're supposed to say approximately, because it's never going to be perfect. And this word right here will kind of keep me good, all right? So approximately normally distributed. The center does not change. The center, it's still going to take me 11.4 minutes, all right? Not me to change the oil. It would take me probably a lot longer. But this 10-minute oil change joint, it's going to take them 11.4 minutes. And then the standard deviation, it's not going to be 3.2. I've got to use my standard deviation formula, the one that said mu over, not mu, sigma over the square root of n. So it's going to be 3.2 over the square root of 35. Now you can pause the video and make sure you're good with that. I have already worked it in my notes, and I got 0.5409. 0.5409. Again, guys, shape, center, and spread. I would be hitting on that so hard if you guys were in here. I would make sure all 19 of you were doing it correctly. All right? Shape, center, and spread on that. Now that we have this that's approximately normally distributed, all right, if I take these 35 next cards that are coming in, I just want to know what the probability is that I get something less than 11 minutes. Less than 11 minutes. Again, let's draw a curve on this. I expect right here in the middle for it to take 11.4 minutes. So whenever these 35 cards come in, I'm just wondering, hey, let's just get it less than 11. So I'm just wanting to know the probability underneath that curve right there. Now, if you have your phone with the graphing calculator app or your own graphing calculator, we can still do this the same way we did last week in class. I'm willing to bet most of you are using tables, so I'm going to go back to using my table. If you're interested in the calculator, have it ready for your Q&A session later this week, and we can definitely hash it out on your phone or graphing calculator. Okay? So I need a z-score. I need to normalize the data. All right? I'm interested in 11. My mean was 11.4, and my standard deviation, my new standard deviation for my 35 cars was 0.5409. I'm expecting a negative z-score this time. I got negative 0.74. That's not my probability. That is my z-score, okay? So that means that I am about 0.74 standard deviations away from this mean right here. To find out what that probability is that my x bar is going to be less than 11 minutes. I'm going to my table. And it's good news. I have the left side this time. I love having the left side because I just have to grab that value off of my table and I'm set. Let's see, where's my table? Keep on talking too much and I forget what my z-score was. Negative 0.74. And I apologize for this being so light. Let me actually go turn my lights back on and see if that will help. Oh, helped for a minute. It's still about the same, right? Let's see, negative 0.74. We're still in here, negative 0.7. And I apologize, you can't see the top of mine. I wanted to be able to make sure you could be able to see where I was at on this chart. So negative 0.74. Actually, let me just move it down so you can see the top of it. There we go. So remember, this is how we are finding it. So negative 0.7, and then I come up here to the 4, and I find where they meet up right here. 0.2296. So this probability right here, 0.2296. Right around 23%, right? So only, oh, I switched slides. Only a 23% chance that this 10-minute oil change joint is going to be able to push out the next 35 cars in less than 11 minutes on average. The average time it takes them to change those 35 cars. I hope that makes sense. Homework's going to be a little bit different this week. And I'm not really impressed with your online book and how they go about this, all right? And I haven't seen SEMO ask questions very similar to how the online book asks it. So I'm going to put this in as a PDF. The answers will be next to the problem. If they're not, just have those. We can go over it during the Q&A later this week. But these 6 problems will go well with this distribution of the sample mean. Have a great day, guys, and I'll be talking to you soon.